get back to the prediction part. I want to make sure that we're on the same sheet of music with this prediction, because everyone uses this word. They equivocate fallacy out of their mind. A scientific prediction is a very specific thing. Are we in agreement?
Sure.
A scientific prediction is a hypothesis. So if you don't have a hypothesis with a viable independent and dependent variable, then you don't have a scientific prediction.
But I would argue that, you know, if, in the example of, you know, force, I would argue that my independent variable would be the mass of the object I'm going to drop. My dependent variable would be the force that it hits the ground with, for example, or the force exerted on the Newton meter when I let go. You know, that's a very clear independent dependent variable.
No, it's not. Do we want to go through this?
Yeah.
We want to go through this?
Yes.
1 second. Let's put it up here so everyone can see it.
And really quick for the teacher, when you say we have observed this, we have experimented, have you been part of the body of science that already presented us this, or you're just adopting what has been presented to you and regurgitating it forward? Because when you say we, I feel like you have been part of it. Right.
Well, I calculate, you know, acceleration of falling objects all the time at work. That's part of my job. We get the kids to do it. I do personally make predictions about how fast something will fall and hit the ground from a certain height, and then I do that, and how the mass will affect it. I make those predictions, and then I calculate it. You know, we do that all the time. So, yeah.
Okay, so if you can click on John's thumbnail in the Hangout, bottom right of the Hangout, just click on John.
Right. Okay. Yeah. Well, that's cool. Right.
Natural phenomena observed, please.
What, sorry?
We're going through the steps right here. Step 1, step 2, and we just need the first 2 steps. So what is the natural phenomena that you observed?
The natural phenomenon is that let's just say a mass will move towards the Earth.
A mass. Now, how do you know mass? Can you see mass?
I can measure mass.
You can measure mass.
Mm-hmm.
How about just things fall to the ground? How about that, so we don't get bogged down here?
Okay.
Is that okay with you? I don't want to.
Yeah,
I don't want to put words in your mouth.
Yeah, no, it's fine. Objects, yeah, but can we put? They will accelerate to the ground.
Okay, so apple falls from tree, accelerates to ground. Happy days.
Yeah.
Okay, so we can go down here, right? Hold on a second. Because your observed phenomenon is your dependent variable.
Yeah.
So we can go down here 1 second. Hypothesis.
I wouldn't say that the objects accelerate is a dependent variable. I would say that the rate of acceleration, or not the rate of acceleration, the force that they accelerate with is a dependent variable.
You can't do that. You're begging the question. Your natural phenomenon is always the dependent variable. It's always the effect. Now we're trying to find the cause of that effect.
Right. So for me, my independent variable in this would be to.
No, I want the hypothesis.
No, so the hypothesis is objects with a bigger mass will accelerate to the ground with a bigger force.
With a bigger mass will accelerate to the ground with a bigger force. You're impugning a force here, but that's all right, no problem. Let's just move on. What is the independent variable?
That will be the mass of the object.
Okay, so mass of the object causes objects to accelerate. Where am I at here? So the mass of the object causes objects to accelerate to the ground
with a different force.
You can't say that because you don't know if there's a force or not.
Well,
You're
when I
just
say force, I'm
impugning
talking about measuring with a Newton meter. So whether you call that a force or not, I'm measuring, you know, with a Newton meter. I'm going to call it a force.
Whoa.
Did you say
We're
Newton
We're not
meter?
going to Newton's meter. So does this make sense to you, or is this just a tautology?
So
Mass of the object causes objects to accelerate to the ground. What have you answered here?
Well, no, I wouldn't. I would say the mass of the object is going to affect the force that I measure on a Newton meter.
That's what I'm talking about. You're already coming up with forces in Newton meters. I mean, it's circular. It's begging the question. The mass of the object. This has to be.
We're talking about weight, aren't we? That's what we're talking about. Objects with a bigger mass clearly have a bigger weight, and weight is gravity times mass. Weight is a force. That's what when we talk about the force, that's what we are talking about. Weight is the force.
So let's just stick with the hypothesis and the experiment. So what's the null hypothesis?
Well, that it doesn't affect it.
Objects that what doesn't affect it?
That the mass will not affect the weight of the object.
Yeah, but we're getting into weight here.
Ramsey, is that you?
It is.
Weight is. I think the definition of weight is weight is the force that I'm talking about. When we times mass by, you know, gravity, that is the formula. That is the equation that gives us weight. So things do have weight. Weight is also directional. You know, we see that all the time. Weight acts downwards. If I sit on an elephant, the elephant's fine. If an elephant sits on me, right, I'm going to get squashed. You know, or if I'm sat on the elephant, sorry, I'm fine. It's not squashing me from below, but it will squash me.
Yeah, but you're talking about weight here. Weight and mass are different. We're into your hypothesis here, and it's just talking about mass.
I'm saying the mass will affect the weight. They are different.
But this isn't telling us why the mass of the objects causes objects to accelerate to the ground.
No, you're right. It doesn't tell us why at all. It doesn't tell us. What we do is we identify the link between the two, and then we ask those questions why.
Yep.
And that requires other experiments and other hypotheses, and it's a long
process. No, we have to do. See, we're not to the experiment yet. We're just trying to set this up because we're going to the experiment right after this.
Hold on, John. But can I just point out what you've done there? So we've not even through, as John has just said, we've not even got to the experiment stage. We're just trying to formulate the hypothesis. And you've already got the answer. You already know what's going to happen and what the cause is. You already know what that force is and what its name is and how it's measured, right?
No, what I've done is I've identified my independent variable, which is going to be the mass. And I'm then going to measure the weight of the object. Right, and as I increase the mass, I'm going to look at the effect of the mass on the weight.
Okay. Do me a favor. Can you define mass?
Mass is essentially the amount of material that you're made of.
And that is not the correct definition of mass. Do you know that
might not
mass?
be the textbook definition, but that is essentially what it is. It's the amount of material that you're made of, whereas weight is the force that you feel when that material is pulled down on you.
Do you see my screen?
Yeah, the amount of matter. It says there.
Nature doesn't. This is from Professor John Wheeler and Edwin Taylor. What is mass? Nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. even if we could count the number of atoms or by any other counting method try to evaluate the amount of matter, like you said, that number would not equal mass.
So what we do is we get a reference point, and we get our, and the standard 1 kilogram masses that are out there. We slapped a number 1 kilogram on something, and we essentially say anything that has twice the mass of this is going to be 2 kilograms. Anything that has half the mass is going to be 0.1 kilograms.
Yeah, but it's not actually mass. Because you haven't defined it yet. I know where you're going with this. I got you. But you still haven't defined it.
To me, it's just the amount of stuff. I mean, we all know things are made of stuff because we can touch stuff. And I'm just saying the more stuff something has, the bigger its mass.
Yeah, but you have, I know. And he just said no.
Air is stuff. Can you touch it?
No, don't go off. He just, and I understand what you're saying. I got you. But Professor Wheeler just said that that's hogwash.
I think that quote needs a little bit of looking into. I think perhaps
it's not a quote.
Interpreting what you're saying there.
It's not a quote. It's a citation, and it's pretty dang clear what he says. Right? And hold on a second. That's pretty clear.
When he says that number would not equal mass, do you mean the number of atoms? I mean, what number?
The number of atoms.
Right. Well, the number of atoms definitely doesn't equal mass because all atoms are different sizes. So like something like uranium has an enormous atom. Something like hydrogen has a tiny atom. So if they're made of the same number of atoms, they're not going to have the same amount of mass.
I understand. That's a straw man. I understand that. But you said it was the number of stuff in something.
Yeah, the amount of stuff. Yeah.
Yeah, so the stuff is atoms. I don't care if they're different weights.
Well, the atoms inside them have protons and neutrons and electrons. That is the stuff. So the number of protons, neutrons, and electrons, then let's define it as that, the number of protons, neutrons, and electrons.
Yeah, atoms.
No. That's like saying the number of bricks is the same as the number of houses, and that's not true. You can't say that I've got 3 houses, therefore they have the same amount of bricks as the 3 houses I've got over here. We wouldn't say that, and it's the same thing here.
Define mass, please.
But let's define it now for the sake of it as the number of protons, neutrons, and electrons. Let's do it that way. But it's definitely not the number of atoms.
I'm speechless.
Those are molecular weights. You don't count them.
I don't care. Let's go back. Let's go back to the hypothesis. All right, because it really doesn't matter. You haven't answered anything here. This doesn't. It's nothing.
Right. When you say that, like I can take an object that has more stuff in it. However you define mass, I can take an object that has more stuff in it. I can place it on a weighing scale, and the force that it presses down is obviously going to be bigger. The amount of stuff does affect the weight of an object.
Okay, you're still calling it a force. I'm going to tell you right now, right, that gravity, the one that the scientific community follows, is not a force.
Hello.
Right? Let me just say this from George Musser in Scientific American. Einstein created his general theory of relativity, which provides our modern understanding of gravity, with the express purpose of expunging non-locality from physics. Isaac Newton's gravity acted at a distance as if by magic, and general relativity snapped the wand in two by showing that the curvature of space-time and not an invisible force gives rise to gravitational attraction.
I think the sticking point is obviously going to be the definition of a force, or the understanding of what a force is, isn't it? To me, like I said, it will change the shape of an object, the size of an object. It will speed things up and slow things down. Now, if you don't want to call it a force, that's fine, but we can't deny that if I take something that's got a lot of mass and it's heavy, and I put it onto an egg, it's going to break the egg. If I put it into it, it's going to crush. It's going to crush a balloon or whatever. There's clearly an action that when I increase the mass, I get a bigger effect from it.
So you're saying mass causes gravity?
No. The gravitational field right? An object in that field is affected. The objects affect each other, and there's a force existing between the two. But you can have the gravitational field without a secondary object. So the Earth's gravitational field. This is why I was asking about potential and potential energy before. Any point of the Earth's gravitational field has a potential, and then when you place an object into that point, depending on the mass, the potential energy of that object will be given. But essentially, and I actually forgot what your question was, and I was waffling on. Sorry, go John.
Well, you said a gravitational field. What gravitational field? Newtonian or Einsteinian?
Well, and that's what we can't explain that at the minute. We can't explain how it works.
Then we don't know the why. We don't know the why. We say gravity. That's why I said anytime that they invoke gravity or say that word, they immediately invoke a cause, whether they know it or like it or not.
I see where you're going. Yeah, I get what you're saying. I think we actually agree. I do. I get where you're going. All right.
Okay.
And I do think I agree in terms of. I was saying before, you've got to ask that question why. You've always got to ask that question why. Yeah.
Right.
Now we do know that when I have something with more stuff, it will weigh more on a weighing scale. But then what you're saying is why. Okay. And that why, when you dig right down, we have to explain exactly the process that's going on to change that, exactly the process that's going on that's causing that object to be pulled down onto the weighing scale. And we can't explain that at the minute. Right. So I understand you're saying, well, why, when we boil right down to it, no, we can't explain what causes that. And I totally agree, we can't.
Well, can I just interject there? Sorry. But hold on, I must interject. So I'm super, super stoked that you've agreed. However, people in the scientism community assert that it is proven with an experiment, in quotes, called the Cavendish experiment.
So the Cavendish experiment, to me, right, would calculate the gravitational constant, but that didn't explain why the two balls moved. It didn't explain the mechanics of how gravity worked. What it did is it gave us something to allow us to constantly make accurate real world predictions and applications that will work time and time and time and again. But
those aren't predictions. They're not predictions. They're not scientific predictions.
Well, when I say what I mean is I like the predictions I make in the lab. If I decide to change the mass of an object I'm going to drop from the ceiling, I know exactly the speed it's going to be traveling at when it hits at the floor, and I use gravitational constant for that. Right. So the number that came out of it does have a use in the real world. But no, I would never sit here and claim that anybody knows exactly what that mechanism is, exactly what that process is. But what I can say is that it is definitely distinguishable from density, and it's not density.
Yeah, well, I never claimed it was density. I don't know. I can't explain it because I can give you an explanation, but in science, the explanation has got to be accompanied by experimental validation.
It sounds as though we're pretty much saying the same thing.
Yeah, somebody's echoing real bad.
Is that my mic? Is that my mic?
No, it's Mona Lisa. Is that Mona Lisa in there?
It sounds as if we are saying exactly the same thing. And I exactly what you said then is what I said before. We always have to go on and ask that question why afterwards. We've always got to do it. And we've got to keep on asking why. But I don't think that we can ignore when we come up with something mathematical that allows us to calculate all the things that we can calculate using the gravitational constant, and then we could see those things happening in real life.
See, you call it gravitational constant.
Well, that's the name of the constant. Now, whether we could call it whatever, the name's relevant, but that mathematics does prove to be true. Whatever you call it, but that doesn't.
I've got to stop you. I'm really sorry to interrupt. I'm really sorry, but it does matter because there are connotations that come along when you call it gravitational. That means something. So,
to me, and I think I'm getting what I think I get what you're saying. Okay, I think when you hear gravity, are you thinking of like a process, a procedure, some kind of like physical process that we claim to understand? Is that what you mean?
No, I mean that the connotations attached to that word are either objects of mass, either Newtonian or Einsteinian, and both involve balls, the Earth, spinning through an infinite space. They're both wrapped around the same bullshit.
Right, so you're linking it to the
Would
shape of the
Al
Earth.
agree? Would Al agree with Professor Reese here? Are you seeing my screen here?
Yeah, what causes gravity and mass? Yeah,
These questions still baffle all of us, right?
absolutely they do, yeah.
So, according to Professor Reese, does mass attracting mass cause gravity? Nope. According to Professor Reese, does space-time cause gravity? Nope. See what I'm saying here? There's built-in contradictions. Once you dig underneath the surface, they already know it, right? He's just telling you straight up right here, right?
Well, I mean, I'm saying exactly the same thing. We can't explain what that process is, and go back, 100 years, 200 years, we couldn't tell you what the speed of light was. There's lots of things we couldn't tell you. I can't tell you now how it works. But we don't have to. There obviously is something that causes objects to have a weight.
No, go ahead and let Al finish. No, go ahead, Al. You finish.
Well, so there is obviously something there that causes objects to have a weight, and the more stuff we put onto a weighing scale, the bigger that weight reads. We know, that the springs are being compressed more in that weighing scale, which demands a force. If I'm going to compress something, compression is a force, isn't it? So there is something there. Now I'm gonna call it gravity, but I can't explain how it works. But when we get the numbers that allow us to make accurate calculations and predictions of what is going to happen.
Predictions again. Okay, sorry.
Oh, you're right. Go on.
No, that's okay.
We get the numbers from falling objects, and we don't ask, well, how did the object get its potential energy? It becomes like an exercise in magic. And then we personify the force as a thing called gravity. Now, if I pick up a microphone and I drop it and pretend I'm not in the equation as giving it the potential energy to fall in the first place, then is that science? Is looking at a bowling ball and a feather on a beam on a roof there, hoisted up by a scissor lift and stuck there with quick release pins, whether you add a red herring of evacuating all the air and making it a vacuum and dropping these objects, do the people who raised them up there and positioned them there and gave them that potential to fall not count? Only magic gravity, as soon as you release them, is responsible. Right back to the apple in the tree. It grew in the tree. The tree, the sun, the photosynthesis stored water and fleshy stuff up there. Not a big mystery. And when it was heavy enough, had enough mass and couldn't be supported by its little stem, it fell. And it wasn't gravity going into the ground, it was stored energy above the ground. Gravity's not involved. If you ask how something got in the air and in a state where it's going to fall in the first place, I
think Al realizes that the problem here is the word, because the word carries baggage with it, and the baggage is not scientifically validated.
Right,
we agree on that, Al?
Sorry to interrupt, because we're just about to have maybe a 5-minute break. So the point of interjection, very valid points, James, and I totally agree with you. You've got to pick the microphone up and put potential energy into it. I completely agree. But the point that John interrupted you was where you said the word prediction, and you had strayed off science into mathematics and then used that word prediction. So we're not talking about scientific predictions anymore. We're talking about Mystic Meg predictions, Nostradamus predictions, not scientific predictions, pseudoscience predictions.
Predictions are not science at all.
Go ahead and let it out.
Sorry, the type of prediction I mean is literally, I'm going to call it a prediction if you want me to use a different word, but if I drop something from a known height of a known mass, I can calculate what speed it will hit the ground at, and I am right 100% of the time. To me, I call that a prediction.
Right, but it's not a scientific prediction, though. You understand that, right?
But it's not a guess. I'm using equations derived from experimentation.
That type of thing is akin to, say, looking at the position of a star over and over for hundreds of years and being able to predict on a certain date where something's going to be. That's not scientific, but it's prediction. But
And
you zero science and only observation to make a prediction.
Jose, that's a really, really good point. And that's the point I make in the video that I put on my channel earlier on. That the reason that the maths, the equations I'm using to make those calculations, to make those predictions, use data that have come from Eratosthenes, that have come from the Cavendish experiment.
That's not an experiment.
Well,
Oh,
the
not
Cavendish,
non-experiments that assume. Ah.
Yeah, I got you. Oh, I got you.
Yeah, we're not talking about experiments again. We're kind of going around in a circle, so I'll probably see that as a good opportunity to round out this show. So I'll say first and foremost, a huge, massive, enormous thank you to all of the live audience for tuning in and hopefully sharing this debate. And of course, a massive thank you to all of the debating panel for making this debate possible. If you hated the show, then you know exactly what to do. But if you liked the show, maybe consider subscribing or sharing with a friend. I've been Nathan Oakley, and I'll see you all in the next video.
Oh, what a day! What a lovely day!